In exercise 1.3, we consider the standard chain ladder assumptions that I have listed on the side here. And we look at the case of non-parametric estimation of fj, which means that we just try to estimate fj directly based on raw data without doing any maximum likelihood estimation and without any assumptions on the distribution of the total claims. So the typical chain ladder estimate is given as such for the estimation of the first coefficient f0. What we do is sum the claim sizes here. So we sum the total claims in this column and divide by the total claims summed in this column. That gives us f0, which we can then multiply onto this claim to get the value of to get the expected value of the total claim in the next development year. And when we go to development year 2, we take this sum and divide by this sum. That will yield f1, which we then multiply onto this total claim in order to get an expectation for this total claim. And we also multiply f1 onto this value in order to get this one. So in the standard chain ladder estimate, what we do is we sum the columns and then consider the ratio. However, in exercise 1.3, we will try to do something different. Instead of taking the ratio of two sums, what we want to do is we want to consider a thing called the development ratio, Fij, which is given for each accident year. So for each accident year, we consider the development ratio, which we find by taking this and dividing by this. So what we wish to do in this exercise is to try and minimize the mean squared error between Fj and a weighted sum of the development ratios. We will try to minimize this mean squared error in Bi. So we will find the Bi tilde values, which plugged into Bi minimizes this conditional expectation, and then use these Bi tilde as weights in the weighted sum of the development ratio, and try and use this as an estimator for Fj. So let's see if this works out. We want to find the coefficients B, which minimize an expression, which we can just call star. So in order to do that, we can set the partial derivatives with respect to Bi equal to 0 and solve for Bi. However, first, let's rewrite the star expression a tiny bit so that it is a bit easier to work with. So you see that the star expression is in fact a conditional expectation of something squared. Recall that the second moment of a random variable can be rewritten as the sum of its variance and first moment squared. So that is what we will try to do here. The variance of this thing inside here conditioned on epsilon j, well, the translation fj does not change the variance, since the variance is translation invariant. So we can just remove the fj term, and what we have is the sum of bi fij over I. And the next term will then be the square of the conditional mean of this thing here. Now recall that the conditional expectation is a linear operator, so it moves inside the sum, it moves inside the constant, and this linear term also moves outside of the conditional expectation, since the fj are just deterministic coefficients. So what we have is the sum from 0 to I minus j minus 1, which that's also the case here, but just didn't write it. There wasn't enough space. Bi conditional expectation of fij given epsilon j, and we subtract fj. Okay. Let's just move a bit further here. We can also take out the summation here due to the fij being independent across accident years, because we have assumed independence across accident years. So thanks to the first assumption in the chain ladder model, we can take out the summation and we can also take out the constants bi, pull them out and square them since we removed them from a variance. And then what we have inside here is just the variance of fj given epsilon j plus an expression involving the conditional expectation of fj given of fij of the development ratio given the information in up until development year j. So what we see now is essentially we just need to calculate the conditional variance of the development ratio and the conditional expectation of the development ratio. So let us just try to do that out here. The conditional expectation of the development ratio is given as the mean of, well, the development ratio, right? So we just put in the definition of the development ratio and note that Cij is measurable with respect to epsilon j, since epsilon j contains all the information from development year 0 to j. So we can take the 1 over Cij outside of the conditional expectation. And apart from that, we can also note that due to the second assumption in the chain ladder model, the conditional expectation of the total claims in development year j plus 1 given epsilon j is just fj multiplied by Cij. So this is equal to fj. We can also do more or less the same with the conditional variance of the development ratio. However, when we take out 1 over Cij from the conditional variance, we have to remember to square it, so squared, and then the variance of Cij plus 1 given epsilon j is just equal to sigma j squared multiplied by Cij, and that is equal to sigma j squared divided by Cij. So if we just plug all of this into our calculations here, then what we have is now a nice expression for the mean square error, where the b coefficients are no longer locked up inside of a conditional expectation operator. Just finish writing this here. So you have bi multiplied by fj, right? And we also have -1 multiplied by fj, so it's just the sum minus 1 multiplied by fj, and then you take the entire thing squared. Okay, so let's take a break here, and then in the next video we will differentiate this with respect to b, set it equal to 0, and figure out which value b minimizes this expression here.